Pythagoras used to have a secret society where he would invite students to listen to his lectures. The only catch is, you had to listen to them behind a curtain until you earned your way to be able to see Pythagoras actually teach. Oftentimes he would teach in white flowing robes with a beautiful crown. His secret society was very helpful to the Pythagorean theorem, although they didn't invent it. This secret society also didn't believe in numbers that were irrational. In fact, one student who dared to explore this possibility ended up mysteriously drowned. Our version will be a little less dangerous, so let's explore the Pythagorean theorem. And we can even remove the curtain to do so. First, we really need to look at the anatomy of a right triangle. Now, a right triangle is defined by having a 90-degree angle. And I always like to mark that 90-degree angle, and I try my best to make a nice little square there. And that helps me to recognize the other parts of my triangle. So the parts where this 90-degree angle that I've marked right here, the parts where it's touching, those are called the legs of the triangle. So it's like the triangle has legs. Sometimes people will interchange that with sides. So each one of those would be a side, but I really like to think of the other side of the triangle as a side as well, so I don't like that term as well. So we're going to use the term leg. Now, not the kind of legs that they're going to walk away. Now, this part that's not touching the 90-degree angle is called the hypotenuse. And the hypotenuse is the longest side of a right triangle. And you can always find it by taking that 90-degree angle and drawing a line, a diagonal line right through it, and it will touch the hypotenuse. That's a good way to remember where the hypotenuse is because it's not always set up like this. Sometimes it's upside down, or maybe it's facing the other way. It's not facing right, it's facing left. So this is a good way to always know where your hypotenuse is. Now, what the Pythagorean theorem says, that is, if we take one leg and we square it and we add it to the other leg squared, it gives us the hypotenuse squared. Now that sounds kind of confusing, so let's draw a diagram to help us see this. So if we square this side, really we're multiplying it by itself. So remember back when you did multiplication by arrays? So we're going to make a square here to represent that leg times itself. And let's call this a variable. We'll use the variable that everyone uses for the Pythagorean theorem. We'll use a. So we take a times a. Now, when we do that, we're actually finding the area of this square. So the area of this square would be a squared. Now let's go ahead and do the same thing with the other leg. And we'll call this what they always call it as well. We'll call this leg b. And we're going to square b, which means we're going to multiply it by itself. So in terms of area, b squared would give us the area. Let's go ahead and label our sides of the square. So b on this side, this is the same as b. We're squaring it. And we'll color it in. Now what the Pythagorean theorem says is that if we take a squared and we add b squared to it, we get the square of the hypotenuse, oftentimes referred to as c squared. Let's go ahead and draw what c squared would look like. So we'll use purple for this. And I need to make sure I go c in that direction. So I have c times c. That's what this cube represents. In terms of area, the area of this square would be c squared. Now if we take a squared plus b squared, that should be the same as the whole area of c squared. And that's what the Pythagorean theorem states. Now surprisingly, Pythagoras did not come up with this idea. This idea had been into practice in China and India. He just really came up with a great mathematical proof of it. And there are actually 350 ways to prove this theorem. So as you get further in your math career, you can look forward to checking out some of these proofs without even having to hide behind a curtain. Now we're going to look at an example. It's not exactly a proof, it's a specific case of the Pythagorean theorem that we can see it works for. So here's our triangle. I'm going to go ahead and draw the right angle in here. And now I can see those are my two legs, and across from that right angle is my hypotenuse. So those are my legs, and if I look at my legs, I have little tab marks right there to show you how many. 1, 2, 3 up there, and 4 across. That's a 3. And then we've got 4 down below. So my legs are length 3 and 4 units. Now I want to look at my legs squared, and I'm going to see if that gives me my hypotenuse squared. So if I look at 4 squared, I have 4 across and 4 down. That's a total of 16 squares. So if I count them all up, 16 squares in here. And I can look at my other side squared as well. So my 3 squared, and that gives me a total of 9 squares. Now I want to show that if I add these two together, a squared plus b squared, it's going to give me my hypotenuse squared. Well, if I look at my hypotenuse, I have 5 units. And so 5 squared is 25. Let's go ahead and write some numbers in here. My legs are length 3 and 4, which means 3 squared is going to give me a total of 9 squares. And my length down here is 4, so 4 squared is going to give me a total of 16 squares. 4 times 4 gives me 16. And I want to show that this plus this is going to give me this, which I put as 5 here. So my hypotenuse length is 5, which means my hypotenuse squared is 25. So let's check to see if when we add the 2 legs squared, if we get the hypotenuse squared. So the 2 legs, 3 squared plus 4 squared equals, well, 3 squared is 9, plus 4 squared is 16, and that gives me 25, which is exactly my c squared. So I showed that the Pythagorean theorem works for this special right triangle. Now, oftentimes we don't want to know what the hypotenuse squared is. We want to know what the hypotenuse is, especially for calculating distance between 2 points. So we can calculate that by unsquaring it, or taking the square root. That's what this radical sign means, square root. So the square root of 25 just asks, what number squared gives me 25? And the answer to that is 5. Also, I can rewrite 25 as the square root of 5 squared, and the square root sign undoes the squared. Okay, so let's look at another example. So if we have legs that are 5 and 12, and we want to find the hypotenuse, we're going to use the Pythagorean theorem to calculate that. Now, in order to do that, we need the square of both legs. We need to square both those legs and add them together, and that will give us the hypotenuse squared. So let's go ahead and do a visual representation again of this. So we're going to square 12. So 12 this way and 12 this way. And that will give us a square with the area of 144, 12 times 12. Units squared, whatever we're talking about. And then we're going to do the same thing with the 5. We're going to draw a square representing our 5 squared, or 5 times 5, with each length being 5. So the area would be 25 units squared. And now we can put in our numbers into the Pythagorean theorem, because we know a squared plus b squared is going to give me c squared. And so my blue square is 144 units squared, and my red square is 25 units squared. And that's going to give me my hypotenuse squared. So I can go ahead and do the calculation. 144 plus 25 is 169, and that equals c squared. That's not c, that equals c squared, so I'm going to have to take the square root of both sides. The square root of 169 is 13 if you know your squares, so 13 squared is 169, and so my answer for c is 13, so this hypotenuse distance is 13, and I can show that that's 13 by using a square with an area of 169. So if I draw my c squared, that area is 169. I know my side lengths have to be 13 and 13. Let's go ahead and look at a problem with real units. I'm asked to find the hypotenuse of this triangle, and this triangle has 4 centimeters on one of the legs and 5 centimeters on the other. I'm going to use the Pythagorean theorem, and I can only do this if it's a right triangle. And if I mark my right angle, my 90-degree angle, that's my only possible one, and I draw a diagonal from it, I know that's got to be C, that's my hypotenuse. And my legs are A and B. It actually doesn't matter which one you label A and B, because addition is commutative, so you could add a squared plus b squared or b squared plus a squared, doesn't really matter. And I'm going to go ahead and put in my values for A. So I have A 4 centimeters squared plus B 5 centimeters, and I'm going to square that as well. And that equals my C squared, my hypotenuse squared. Now I'm going to go ahead and do the calculation. I have units in here. We're going to be careful with those. So I have 16, 4 squared is 16, and centimeters squared is centimeters times centimeters, or just centimeters squared. And then I have 25, 5 times 5, and centimeter times centimeter, that's centimeters squared, and that equals my c squared. Now I'm going to go ahead and add 25 and 16, and I get 41. So I have 41 centimeters squared, and that equals c squared. Now, I'm going to take the square root of both sides, but 41 is not a perfect square. So if I don't have a perfect square and I can't simplify the radical, I'm just going to leave that inside the square root sign. So 41, and then the square root of centimeter squared is just centimeters. So this length right here is the square root of 41 centimeters, and that's more than 6 and less than 7, so somewhere in between there, as I have my length. So let's look at another example you might come into contact with. Now notice this is not situated like our other right triangle, so we need to find the 90-degree angle and figure out what we're even solving for. So we'll remember the Pythagorean theorem because we do have a right triangle, and a squared plus b squared equals c squared. And we'd have to be given that this was a right triangle, since that could very well be 91 degrees. So somewhere in our problem, we would have to know that that's a square corner. Now, we've got to figure out what we're going to solve for. Are we going to be solving for the legs, or are we going to be solving for the hypotenuse? So let's draw our little square corner here, and that will give us some insight. So the square corner, remember the square corner is touching the legs, and that's the hypotenuse. So I know the hypotenuse this time. So my 7 must be my C. C is always representative of the hypotenuse. So I can go ahead and put a little C there to remind myself. Now I can choose which one of these is A and which one of these is B. It doesn't really matter. I'm going to label that one B and that one A. And so now I'm trying to solve for A squared, not C squared. So I'm not just going to add those two squares together. So A squared I don't have. I'm just going to leave the variable there. Plus B squared I know is 6. So I'm going to substitute that value, 6 inches squared. So I'll put 6 inches for that. And then I know my C as well. That's 7 inches, and I'm squaring that. So I have A squared plus 36 inches squared equals 49 inches squared. Now I'm going to solve for A squared. So I add negative 36 inches squared to both sides. And on my left-hand side, that just leaves me with an A squared plus 0, or A squared. And that's equal to 13 inches squared. Now remember, that's not the length of my leg A. That's A squared. So I have to take the square root of both sides. So then I have A equals the square root of 13 inches. The square root of inches squared is inches. and that's approximately equal to 3.6 inches.